An overview of sequences and series, narrated by Dr. Rebecca Swanson, Colorado School of Mines. In this video, we are going to define sequences and visually represent them with graphs. A sequence is an ordered list of numbers of the form A1, A2, A3, etc. We often use bracket notation, bracket a sub n from 1 to infinity, or just bracket a sub n to also notate the sequence. In this definition, a sub 1 represents the first term, a sub 2 represents the second term, a sub 3 represents the third term, and so on. Let's look at a few examples of sequences. In this sequence, the first term is 2/3, the second is 4/9, the third is 6/27, and the fourth is 8/81. The dots imply that some pattern is continuing. We could probably guess the next term. The numerators, 2, 4, 6, 8, indicate that the next numerator should be 10. The denominators, we have 3 to the 1, 3 squared, 3 cubed, and 3 to the 4th, indicate the next power of 3, or 243, should be our denominator. Although it isn't always possible to write down a numerical formula for a sequence, it seems that we should be able to do so here. So let's try. Again, the numerators, 2 times 1, 2 times 2, 2 times 3, 2 times 4, etc., indicate that in general our numerator formula is 2 times n. We already saw the denominators have the form 3, 3 squared, 3 cubed, etc. So the denominator of the nth term should be 3 to the n. Thus the formula a sub n equals 2n over 3 to the n seems correct. Of course, we can always check it by plugging in n equals 1, 2, 3, 4, etc. to make sure it matches the terms we have here. In this sequence, we see the first term is 2, the second term is 4, third term is 8, and the fourth term is 16. We can again probably guess that the next term, since we're doubling our terms each time, should be 16 times 2, or 32. Also, we should be able to write down a formula for the sequence since we've noticed this pattern. We again see that we have 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, so we can conjecture a sub n in general is 2 to the n. In our third example, we see that we have a pretty basic sequence. Our terms seem to be alternating between 1 and -1. Note that the formula a sub n equals -1 to the n plus 1 works, since plugging in 1, 2, 3, 4 for n gives us these terms. -1 to the squared is 1, -1 cubed, -1 to the 4th, and -1 to the 5th give us these first terms, and we'll continue alternating. However, we could have also set a sub n equal to negative cosine of n pi. Since we plug in n equals 1, we get the negative cosine of pi, or negative -1, giving us our first term. When we plug in n equals 2, we have negative cosine of 2 pi, which is -1, etc. So this example shows us something else about sequences. Not only are they ordered lists of numbers, but they also could have multiple formulas. Now our last example shows us something else that could come up. Here we have a sequence 3, 1, 4, 1, 5, 9, which you might recognize as digits of pi. So we can explicitly describe a sub n to be the nth digit of pi, but we're not going to actually get a formula like in the previous instances, since pi is an irrational number that is never ending and never repeating. Now most of the examples that we will work with in this course will have nice formulas that we are either given or must find. In class, we will discuss some of the reasons we might care about sequences, but for the remaining time in this video, I want to discuss the end behavior of sequences. In our applications, knowing what happens to a sequence in the long run, or as n approaches infinity, will be very useful. Soon, we will develop a notion of a limit of a sequence, which we're going to write in this way. what's going to happen as we increase the n value to infinity. But for now, we can at least speak intuitively about such limits. And this is where having a graph of a sequence will come in handy. To graph a sequence, we'll think of our x-axis representing n values and the y-axis representing sequence values. And we're going to plot points of the form n a sub n, where n is a whole number. So let's graph our first example. I'm going to be plugging in 1, 2, 3, and 4. And we can keep going from there, but let's just start with those values. And if I look at my values, when I plug in 1, I should be getting 2/3, and my numbers are getting smaller. So I probably want to scale the y-axis so that 1 is pretty high up. And so here's the point 1, 2/3. Next we have, when n is 2, we have 4/9. We have 3 and then 6/27, which is even further down. And 4, 8/81. So here's the graph, at least of the first part of our sequence. And what I want to point out is that the graph is really just a bunch of dots. However, it seems that those dots are approaching 0, so we might conjecture correctly that the limit is 0. And again, we'll learn how to verify this later. Let's look at our second example. Here the values of our sequence are getting large, so we're probably going to want to start small here. And we have 1, 2, 2, 4, 3, 8, and then 4, 16. And again, we can make a conjecture that our limit will be infinite. Now let's graph our third and fourth examples. In the third example, we're just bouncing back and forth between 1 and -1. So we have 1, 1, 2, -1, 3, 1, and 4, -1. Here we have 1, 3, 2, 1, 3, 4, 4, 1, 5, 5, 6, 9. In both cases, we have some oscillation and our terms are never leveling off to some value. So we might conjecture the limit does not exist. These four examples show us the possible end behaviors or long-run behaviors of sequences. We either will end up getting a constant limit, an infinite or negative infinite limit, or having a limit that does not exist. So at this point, we know what a sequence is. It's just a list of numbers in some order. And we can graph sequences and possibly conjecture what's happening as n increases to infinity. Before we finish, though, I want to make one last comparison in the context of example 1. So in example 1, we had our sequence a sub n, where a sub n is 2n over 3 to the n. We graphed it by plotting points of the form n, 2n over 3 to the n. And again, remember that n represents whole number values. Now let's compare this to the real value function f of x equals 2x over 3 to the x, where x now represents real numbers. Now if I graph this function, I have a continuous function defined for all real numbers, and its graph is of the form, has points of the form x, 2x over 3 to the x. So the graph of this function is not a bunch of dots, but the comparison between these scenarios is that f of x would connect those dots. So note that not all sequences have these nice functions that connect these dots, so we have to be a bit careful when comparing sequences to functions. Since the inputs of a sequence are whole numbers, our sequence graphs are always discontinuous. What that means for us is that we still need to further study the behavior of sequences, since most of our work with limits in Calculus 1 required continuity.